4.4, concavity in the second derivative test. Definition of concavity. Let f be differentiable on an open interval I. The graph of f is concave upward on I when the derivative of f is increasing on the interval, and concave downward on I when f prime is decreasing on the interval. So here is an example of concave up. Here, the derivative of f is increasing. Okay? So, look at the derivatives here. It keeps increasing. So this looks like it's possibly negative, then it's getting positive, then it's getting even more positive. Here is concave down. Here, f prime is decreasing. Okay, so the test for concavity. Let f be a function whose second derivative exists on the open interval I. 1. If the second derivative of x is greater than 0 for all x in I, then the graph of f is concave upward on I. 2. If the second derivative of f is less than 0 for all x in I, then the graph of f is concave downward on I. Finally, number 3, if the second derivative of x is equal to 0 for all x in I, then the graph of f is neither concave upwards or downwards on I. So these are the tests that we're going to use here in a minute to figure out concavity. Definition of points of inflection. Let f be a function that is continuous on an open interval. Let c be a point on the interval. If the graph of f has a tangent line at the point c, f of c, then the point is a point of inflection of the graph of f when the concavity of f changes from upwards to downward or downwards to upward at that point. So this is a point of inflection because concavity changes. Here it's concave up, here it's concave down. Another example here is point of concavity. This is concave down. This is concave up. Again, concavity switches. Again, point of inflection. This is concave up. This is concave down. Point of inflection, concavity changes. Points of inflection. If c, f of c is a point of inflection of the graph of f, then either f double prime of c equals 0 or f double prime of c does not exist at x equals c. So let's look at the first example here. Determine the open intervals on which the graph of f of x equals e to the negative x squared divided by 2 power. So let's think of this as being e to the negative 1/2 x squared power. So first of all, we need to figure out the domain. It gives you a hint here. It probably will not give you this hint on a test, but the domain of this function would be all reals. Whatever you plug in here would give us a real solution. All right? Okay. Next, we need to find the first derivative. So f prime of x. Let's take the derivative here. We know the derivative of the e to the x function, or e to the u, would be e to the u times u prime. So this is going to be e to the 1/2 x squared power, and then we need to take the derivative of the power. So we need to take the derivative of this, which would be negative 1 x. So this is going to be negative x e to the negative 1/2 x squared power. Now we need to take the second derivative, because to find the points of inflection and to figure out concavity, we need to use the second derivative test. So let's take the derivative of this. This is going to be the product rule. So it's going to be the first, which would be negative x, times the derivative of the second. Well, the derivative of the second is taking the derivative of this guy, which we already found, which is this. So this is going to be negative x e to the negative 1/2 x squared plus, so the first times the derivative of the second, plus the second times the derivative of the first, which would be negative 1. So now let's simplify this. The second derivative of f of x equals negative x times negative x would be positive x squared e to the negative 1/2 x squared power minus e to the negative 1/2 x squared power. Now I can factor out e to the negative 1/2 x squared power, leaving me with x squared minus 1. And then this is the difference of squares. So I'm going to have e to the negative 1/2 x squared times x minus 1 times x plus 1. Okay, so to figure out the possible points of inflection, they're going to exist where f double prime of x equals 0. Okay, all the x values that make that true. Or where f double prime does not exist. So first of all, let's take the second derivative and set it equal to 0 and solve for x. So here, hopefully you can see that x would equal 1 or x could equal negative 1. Okay? If I tried to figure out x values where this would be undefined, there are no x values that would make the second derivative undefined. So these are my possible points of inflection. Now I need to test them. So this is how I test them. So draw a number line. Represents the domain, so from negative infinity to positive infinity. My possible points of inflection are at negative 1 and at positive 1. And I'm going to look at these intervals here to see if it's concave up or concave down. If concavity switches at any of these intervals, then where it switches at, that point is going to be a point of inflection. So let's test this first interval. I can test f double prime of negative 2. So when I plug in negative 2 into here, when I plug negative 2 into here, no matter what I plug into there, no matter what I plug into here, this is always going to be positive. Okay, because that squared is always positive. So that's positive. Negative 2 here, that's still going to be negative. Negative 2 here, that's going to be negative. So positive. So I've got the first scenario. I've got a positive times a negative times a negative. So that's positive. So this is going to be greater than 0. So this is going to be concave up. Next, I'm going to try f double prime of 0 for this interval. Okay, that's going to be 1. So I'm going to have 1 times negative 1 times 1. That's going to be less than 0. So this is going to be concave down. I think this is going to be point of inflection. Finally, this last interval, I'm going to pick 2. So f double prime of 2. Remember, this is always going to be positive. So that's going to be positive. Put 2 in here, that's going to be positive. Put 2 in there, that's going to be positive. Positive times positive, positive is greater than 0. So this is going to be concave up. Okay? So because concavity switches from here to there, that point there is a point of inflection, and same here. Concavity switches again. So, inflection points at x equals -1 and x equals 1.